When building multi-threaded applications, developers face a core architectural challenge: transferring data between isolated execution threads without causing corruption. Traditional systems programming typically solves this by having threads share the same block of memory. But shared memory requires complex lock management, like mutexes, which frequently leads to data races or runtime crashes when multiple threads try to read and write at the exact same time. Languages like Rust and Go adopt a different approach. Do not communicate by sharing memory. Instead, share memory by communicating. To see how this works in practice, we are going to architect Rust's mpsc channel from the ground up. We will look at how this structure pairs with strict ownership rules to guarantee safe, concurrent data streams. Understanding this message-passing architecture reveals exactly how Rust achieves its promise of fearless concurrency, completely bypassing the overhead of manual memory locks. The foundational tool for message passing in Rust's standard library is the mpsc module. Calling mpsc.channel returns a tuple dividing into two halves. The first is tx, the upstream entry point for pushing data. The second is rx, the downstream exit point where the main thread consumes it. The channel relies on both of these halves existing. If either the transmitter or the receiver is dropped by the system, the entire channel is instantly considered closed. This strictly unidirectional pipeline physically segregates the sender and the receiver, forming the architectural basis for safe cross-thread communication. To make use of this channel, we need to run parallel computations outside our main execution loop. We do this by instantiating a new thread using the thread.spawn function. This diagram illustrates the memory boundary between threads. To cross that gap, the move keyword takes complete ownership of the transmitter. Now secured in the new thread, calling send pushes a discrete message into the pipeline. Because the receiver on the other end might have disconnected before the message arrives, send returns a result type. This forces us to implement explicit error handling, typically by calling .unwrap for simple applications. By moving the transmitter into an isolated thread, we bridge the execution gap. Background processes can now safely feed data back to the main application asynchronously. This raises a critical question. What if the sending thread modifies the local variable after it has been sent? In many older systems languages, this creates a race condition. Two threads attempting to access the exact same memory space simultaneously causes silent corruption. Rust solves this using move semantics. Executing send enforces a transfer of ownership, stripping the token from the transmitting thread. Any subsequent attempt to borrow that variable triggers a fatal compiler error. While other languages might allow the program to compile and potentially crash later, Rust stops the error immediately. This compile time intervention removes the possibility of race conditions, enforcing data safety before the code ever runs. With data moving safely through the pipeline, we shift focus back to the main thread, where the receiver waits to consume incoming messages. This timeline maps the main thread's execution. The receive message completely halts the execution flow, sitting idle until a message arrives. Alternatively, try-receive is a non-blocking poll that instantly returns a result, allowing execution to continue. Try-receive is critical for applications where the main thread must process other ongoing work, allowing it to maintain its loop while occasionally polling for background messages. Alternatively, if we expect a continuous, predictable stream of data, the receiver can be utilized directly as an iterator within a standard for loop. Understanding when to block versus when to poll allows developers to precisely tune thread idle time against the unpredictability of incoming asynchronous payloads. The mpsc module stands for Multi-Producer, Single Consumer. The architecture naturally supports multiple distinct threads sending data to a single receiver, but we face a structural limitation. Because of strict ownership rules, a single transmitter handle cannot be moved into multiple spawned threads simultaneously. Calling .clone on the original transmitter generates identical sending handles. Now, independent threads take exclusive ownership of their respective transmitters. Messages from both enter the single pipeline, arriving non-deterministically based on operating system scheduling. Cloning the transmitter safely scales the workload across multiple CPU cores, funneling all parallel results into a centralized single consumer choke point. Zooming out, we can see the complete system architecture, multiple isolated threads, each utilizing a cloned transmitter, funneling asynchronous data into a unified stream. This message passing paradigm entirely steps the need for complex manual lock management over shared memory states. The safety of this entire system relies on the compiler. Strict move semantics guarantee that data cannot be unsafely mutated by the sender once it enters the channel. Downstream, the receiver flexibly handles the incoming stream through either blocking halts or continuous non-blocking pulling. By aligning architectural pipeline patterns like mpsc channels with ownership constraints, Rust enables the construction of concurrent systems where memory safety is enforced by the language itself.